Okay.
In the sky.
My face isn't even in
In the
there.
sky over New York.
So, like I said, we're in our review mode. We all know this. I have a lot planned today. I told you guys I want to make sure that I'm planning things that are really useful for you guys. So today we're going to spend a little time talking about the equation sheet. I'm going to take a little bit, kind of help you maybe get a better grasp of the AP equation sheet, which is going to be a key resource when you take the test. I have check-ins that I'll do at the end of class. I want to review Unit 1. I want to go back, look at kinematics, our very first unit. It was just on motion. That's what kinematics is. I want to review that stuff. I then have, I found a really great resource. It's a AP Physics 1 workbook. It's like 300 pages. Don't worry about it. It's really, really nice because the value that I see in it is it breaks down multiple choice questions and FRQ questions by unit. So it's going to help you today. I'm going to have some multiple choice questions that we'll do to practice in class, but we can pull them from that workbook and pull them straight out of Unit 1. All the questions are focused on Unit 1 that we want to talk about reviewing. There's also, at the very end, I'll do practice FRQ, maybe 2 of them. But again, those come from Unit 1 and maybe 2. But today, we're focused on reviewing Unit 1, doing some practice problems for Unit 1. We'll do an FRQ. And then I'm going to assign you guys homework to keep practicing. But I'm going to let you guys pick the problems. This workbook that I'm going to give you, again, I can't print one out for you guys. That'd be like 30 pages per student. So I'm going to have a digital copy. But the homework, I'm going to have you guys pick like 10 questions from Unit 1 and Unit 2, or maybe just Unit 1, that if you bring back to me, like, hey, I did questions 11 through 20, and you bring back your work and submit it, I'll give you points. All right? We need to be, I know I don't often give homework, and I probably should have done a lot more homework, but I think we need to be practicing outside of just my class. I don't think showing up for 90 minutes and leaving and coming back in 2 days is enough prep time. I don't think that's efficient use of your guys' time. You guys are going to have to start putting in a lot more work as we get closer and closer to get yourselves ready. I can only manage this 90 minutes, but then I want you to be working on something outside, and so this is a simple way of letting you choose, but I want you to show me that you actually did some work, some practice for Unit 1, and then we'll try and maybe follow that schedule. Do you want to follow a schedule where we take like 2 weeks to just review? Or do you want to like do a Unit 1 review and then do a lot of FRQ practice? Then Unit 2 review? Any input on?
I think homework is just going to make my grade work, like really main important things. Same thing with the other units.
Okay. That was in my head what would be the best choice, going unit by unit. So today, all about Unit 1. We'll review. We'll do practice questions in class, check them. We'll do practice FRQ and check it. We won't do the official grading, all right? And then I'm going to have you guys do homework where you guys are going to pick another set of 10 or whatever Unit 1 problems that you're going to do, bring them back to me, and I'll give you credit for that's your homework. All right, so we're going to really hammer home Unit 1. All right, first thing I want to do, I want to try this exercise with you guys. I want to try and help us get a better grasp of this equation sheet and how it will be useful to you. So I want to take a second. I'm going to give each of you guys a fresh blank copy. What I want to do is have you guys highlight which equation belongs in which unit. I want you to start exercising. I think this will be a good task, right? I want you to look at an equation, and I want you to tell me which unit, what topic is this for? One, it's going to force you to understand, like, what is this equation? Oh, this is the equation for momentum. I wonder what unit that goes with. Momentum. I have highlighters and colored pencils. If you're really particular like I am, I like color-coded mine. I got colored pencils to give lots of options. You could be underlining. Like, hey, teal is for Unit 1. I want you guys to attempt to make like a little answer key and select which equation belongs with which unit. Or you could, if you wanted to, right beside each equation, write out like, oh, Unit 1, Unit 3. I want to remind you guys, our unit list, it's up here on the board. Otherwise, if we go to classroom, right at the very bottom, I don't think schedules is it. Nope. You can either use the big ideas list. This says Unit 1 is kinematics. Unit 2 is dynamics. Otherwise, you could pop open the syllabus, which I'm sure you guys haven't looked at in months. To be fair, I haven't either.
I don't even know what syllabus you're talking about.
The syllabus for the class.
Don't know
Right.
You know what a syllabus is, right?
Yeah.
Okay, so it's that syllabus. It's just, I have a list, I have a schedule of Unit 1 was kinematics, Unit 2. So if you're forgetting like Unit 2, I don't know what Unit 2 was. Oh, dynamics. I remember dynamics. Right? So I want us to take some time and I want you guys to practice identifying what is this equation and what topic would I use this equation in. I want us to start to try and link together equations. I'll let you use your notes. Right? I want you to try and do this from memory because you're not going to get notes on the test. I want you to try at least look at the first one. Right? Does anybody know what unit would that very first equation come from? Maggie's saying Unit 1, kinematics.
Yeah, I'm saying
We agree with that? I would agree with that. Right? That equation we learned about in Unit 1, kinematics. It was motion, position, speed, and acceleration. That equation is all about speed and acceleration. Right? So I want you to try and practice. First, try on your own. What can you do from memory? Like, oh, I know this is momentum. It goes to the momentum unit. Then, bust out your notes. Use those to help you. You can use this to help you from the get-go. No, that's all right. I don't want to be a hassle. Plus, you have it like pretty stretched, and I don't want to bump it or nothing. All right. So again, just take some time. Go through this and start to try and identify what equation would I use for what type of question, what unit. I want to give you guys some time. Try and test yourself. Have this be an exercise to help strengthen your kind of understanding and do it from memory. What equations do you remember and which unit would you use them in? Label them, color code them. I have more highlighters that you can use. I have more colored pencils that you can use. Whatever you want. I want to give you guys time to start that. If you remember, like, oh, I remember like a third of them, right? Then bust out your notes. Start using resources and trying to identify what the equation is and what unit it goes towards. After a bit, I'm going to come together and I'll show you my choices, right? What I would say these go with. There are some equations that you could argue between a couple, right? But I just want to give you kind of my answer, right? If you're completely lost, looking at mine, hopefully you can jot down some notes or jog your memory. Right? I just want us to make sure we're familiar with the equation sheet. And I have a bunch of extras if you need them too. So if you wanted a blank copy or maybe you wanted the second version that you do from my key, whatever you want, I got extras up here. So I'll stop talking. I'll let you guys, again, identify, highlight, just right off to the side, like this one's Unit 1, this one's Unit 2. Again, if you don't know which unit is, you could just write the name. Oh, this is a kinematics equation. This is a dynamics. Unit 3 is circular motion and gravitation. Unit 4 is energy. It's a really big one. Unit 5 was momentum. Unit 6 was simple harmonic motion, right? Like pendulums, spring oscillations, repetitive motion, I guess. And then 7, our last unit was torque, twisting force. and then rotational motion. Andre, what are we doing? Come on, please focus up. If you're color coding or something, give yourself like a key at the bottom. Like unit 1 is purple, unit 2 is green, whatever it is. Otherwise, just label off the side. Yeah, like doing numbers also works. Maybe give yourself a key. It's up to you, but in my mind, like have down here 1 equals kinematics. That way it helps make your mind connected. Oh, these 3, these 1, kinematics, motion equation. I just want us to practice using this equation sheet, knowing what's on it, knowing where stuff's at. So this is a quick tool to use rather than a big list of messy equations that you gotta relearn as you go through or something. You want a little more time, or you don't want to just talk about them? Talk about them? Okay. All right. And again, if that was difficult and you were like, oh my gosh, I don't know where these equations are, or I don't remember what this equation was, let that be assigned to yourself. Oh, I need to get familiar with this AP equation sheet, or, oh man, I really need to pay attention when I review, because I don't even remember what the kinematics equations looked like. All right? So I want to show you my version. I'm not saying mine is absolutely right. I think it's pretty darn right. I want to quick remind you, there's 2 pages to your equation sheet. The first page is a bunch of constants and conversion factors, unit symbols, there's prefixes, right? If it says you have a megawatt, that means you have 10 times 10 to the 6th watts. So it gives you your units, so you don't forget those. And it also has some very important notes that I actually didn't notice until I did this assignment, or this activity, when I made my answer key. On the test, there are certain things that are always assumed. The frame of reference for any problem is assumed to be the inertial frame of reference, meaning whatever, like you're on planet Earth. That is your frame of reference when you look at motion. Now, certain questions might say, assume you stand on the train as it moves. What type of motion do you see on the train? That's telling you a different frame of reference. Your frame of reference really matters for motion. Right? So that's something that's always assumed. Another thing, air resistance. Always assume it doesn't matter. If a question's wanting you to think about air resistance, it will tell you explicitly. But for any problem, you always assume, we're going to ignore air resistance. We're going to consider it small enough that it'd be 0. In any situation, positive work is work done onto a system. Do you guys remember what the definition of work was?
Wasn't it the distance done to an object or something like that?
Distance, yes, absolutely.
And then it was force?
Yes. Work is when you push on an object a force over a set distance. This note is saying when you figure out, like, oh, I did work on the system and the system did work elsewhere. What's the total work of the system? Positive work is stuff that happens to the system. This should make sense because when you do work, you're giving energy. You need to use your energy to do work, and that energy goes into the object that you're doing work on or pushing on. So when you find out the total, positive and negative matters. If you tell me negative 10 joules of work, you're telling me the system lost energy. If that's not what happens, that's wrong. So I always assume when you do work onto something, that is positive energy. It increases the energy of that system. Number 4, you don't need to worry about. This is units 8 and 9 with circuits and electricity. You don't need to worry about that. And batteries, you don't need to worry about. I should have crossed those 2 off in my... Darn it. Oh well. So that's that first page. I don't want you to forget that there's unit symbols. There's a couple constants that we use. Gravitational constant is big G. Gravity is 9.8. Now, right here. So if we're looking at, again, my answer key I color-coded. So first of all, we can talk about, I guess, kinematics. Mine is this golden yellow. These first 3, definitely kinematics. Straight off the bat. You got velocity, position, and acceleration. Those are all kinematics topics. Kinematics was just about motion. Position, velocity, acceleration. First 3 are kinematics. I also highlighted that AC. Anybody remember what this one is?
I think that was the first one. Part of the
Centrifugal acceleration.
Okay, 2 things. Josh, what?
Is
the first one you have highlighted, is that part of Unit 1 or Unit 7?
Unit 1. The golden yellow is 1. I have this. Yeah, I get what you're saying. On my paper, it's super clear.
Yeah.
This is it's like a pale yellow. These are my golden yellows. Yes, I apologize. The scan, when you look at mine, it's super clear. There's like a fluorescent yellow and a golden yellow. On the scan, it's not as clear. Golden yellow, basically the yellows at top, are kinematics. These bottom yellows, they're supposed to be this pale, like highlighter, like fluorescent yellow. That's Unit 7. I apologize for that. I wish the scan was better. Brody, what were you saying? This equation down here?
Centripetal acceleration.
Bingo. A sub c, that's centripetal acceleration. That was motion. V squared over r. So these 4 equations, I selected, those are our kinematics. It was all about motion, and that's it. We didn't even talk about forces at that point. All we cared about is how do things move? What's their speed? What's their acceleration? What's their position? Those are the only 4 that I selected for Unit 1. Unit 2, I put in orange. Can anybody summarize what dynamics is? What does that mean? What was dynamics? Force. That's actually a good summary. Kinematics with forces. Dynamics was looking at motion, kinematics, but thinking about the forces behind it. So, obviously, anybody know what the name of this equation is? One of the most important equations in all of physics. F equals ma. It's written A equals force over mass. If you multiply mass over, F equals ma. This is typically how true physicists like to see it. Because that's like the common form that caught on. But for us, we learned about position, velocity, acceleration. So let's connect acceleration to the forces. Right? We know acceleration, that's what we start with. Now let's use that to get to a new piece of info. That's oftentimes why it's phrased like that. Newton's second law. That's all it is. F equals ma, or, this is rewritten, all the total force divided by mass gives you the acceleration. And then down here, frictional force. Remember that? Again, F sub F is the friction force. Friction force is coefficient of friction times normal force. Right? That was another force that we learned about that affected the motion. Down here, I highlighted the spring force. The very bottom. That was another force we talked about. This is Hooke's law. The force on a spring, this is in the very bottom left of your sheet, is equal to the spring coefficient, how stiff that spring is, multiplied by how much it was stretched. Tells you how much force is in the spring. And then, force of gravity is mass times g. Again, they rewrite it as the acceleration of gravity is force of gravity over the mass. So those orange ones were the dynamics ones. Essentially, it was all the forces that we learned. That was my Unit 2. Unit 3, circular motion, and then universal gravitation, I did in pink. This down here, this is our universal force of gravitation between any 2 objects. This is not just Earth anymore. This was Earth. This equation in the kind of bottom right, this is the force of gravity between literally any 2 objects. So when I ask you, like, hey, this planet exists, how much force does it exert on you? Well, the universal force of gravitation is big G. You do not need to know that number. Scroll back up to your equation sheet. And there it is. Right there. Just plug it in. Times the mass of object A, maybe that's the planet, mass of object B, that's you, and you divide by R. What does R represent? Yes, the distance from object to object, right? So that was universal gravitation. I also highlighted these equations. What are these equations? Huh? Yes, it's the same thing as a kinematics equation, but with circular motion. You could also put this in Unit 7, because Unit 7 we talked about torque and rotational motion. So we kind of reviewed this stuff. These are exactly the same as these equations. But these equations apply to circular motion. Right? Theta, that's your position. When you talk about circular motion, it's talking about how much have you rotated. What rotational position are you? Omega, how fast are you rotating? And alpha, looks like a weird squiggly A, or kind of like a fish sometimes. That's how much is your angular speed changing. It's angular acceleration. So the pinks, those are what I did for Unit 3. Circular motion and universal gravitation. Circular motion, universal gravitation. Unit 4 was energy. Really big one. Big, important topic. There's quite a bit of them. Actually, I'll start right here. Over on the left middle, what's this? Kinetic energy. 1/2 mass times velocity, squared. This is conservation of energy. When you have a system, whatever energy is in that system does not change. If it does change, that means you sent energy out. The change in energy on the system, if energy comes in or energy comes out, work was involved. Work is transferring energy. Work is defined as force times distance. Technically, I could have highlighted this section for... Actually, no, we talked about work and energy. Never mind. That's the definition of work. This equation, work, is equal to the change of energy in a system. The change in energy of the system over time is what? No. Work and, or the two topics. What was work over time? It's a P.
Oh, wait, it's power.
Power. Work and power go hand in hand. Power is how much work you do per time. Change in energy is work. One thing I would recommend, when you get your equation sheet, just write over here, power also equals W over T. The literal definition of power is work over time. They write it as change in energy over time, which is correct, but that change of energy is the work. That could be a helpful first step. All these potential energies are coming in. What's this one up here? Gravitational potential energy. If something is off the ground, it has potential energy. mgh is how I always memorized it, but delta y is how high is it off the ground. All right? What is U sub s? Spring energy. The potential energy in a spring, the stored energy when you squish a spring, is 1/2 K, the spring coefficient. How stiff the spring is, times the position, how much it was compressed squared. And then this guy, this is universal gravitational potential energy. Right? We're not looking at the energy compared to the planet Earth. We're looking at what kind of potential exists between two planets. That if we let them go, what would their gravitational potential energy do? All right, so you have that equation. Okay? Yes, and I think I did. Did I not? Yeah, let me add. Oh, I did forget that. Thanks for mentioning that, because here we go. Hope that's the right one. Yes. Okay. Unit 5, momentum. I put it in blue. There's not a ton of equations. We have the equation for momentum. It's a lowercase p. I learned it as a rho, but actually, AP Physics, they use the rho, the weird p, for density. I don't like that, but they have it set up. This guy at the bottom is just...
forbid everybody be on the same page.
Well, typically they are, but there's subtle differences. This equation you probably won't use, but it's the density of an object is mass over volume. But we don't need to do that. We're doing momentum. P, the momentum is mass times velocity. The change in momentum, do you know what that was called? Impulse. Impulses change momentum. What an impulse is a force that acts over a certain time period. If you apply a force over a certain time period, you've created an impulse that changes the momentum. Delta P. Those are the only equations that I saw for momentum. Momentum is a big chunk of the test. There's a lot of questions about it, right? But there's not a lot of material or equations, rather. I ran out of highlighter colors. Unit 6, I squared in purple. They're all bundled up together. Unit 6 was simple harmonic motion. Spring oscillation and pendulums. Simple harmonic motion was like a set repeated motion. Typically they're coming as springs or pendulums. I have a sneeze, but it's not coming. Oh, dang it. It's got to bother me. You guys remember what capital T is?
Period.
Period. Bingo. John, how'd you know that?
Because I looked at the sheet.
Yeah, good, good. Your sheet tells you. It's got all these letters. I should show you up here. It tells you what the letters are. If you look at AC, what on earth is AC?
EAC.
Oh, go figure. That's the one that...
He's talking about
Go figure. What's A? Acceleration. Then you should be able to think like C. Oh, we talked about centripetal. But anyway, yes, capital T, it tells you, oh, that was the period. You guys remember what the period was?
It's the same as impulse.
No, not impulse. Period was the time for one oscillation. The pendulum swings. How long does it take to go from one end back to its starting point? That was the period. The time it takes for one oscillation. You could take... Yeah, 1 over frequency is period. And 1 over period is frequency. You have that relationship right here. The period of a spring... It's 2 pi, and then the square root of m over k. It only matters between mass and the spring constant. Pendulums, all that matters is the length of the spring and then gravity. So you have your simple harmonic motion equations right there. Last one, unit 7, torque rotational motion. This should be fresh. Again, this is like the neon yellow. Doesn't show up super well, but it's all of these. All the yellow on the bottom is my neon yellow. Notice I re-highlighted the circular motion stuff because we're talking about torque, twisting motion that creates circular motion. We go back to Unit 3, circular motion. The rest of these are specific to circular motion. We have Newton's second law for rotational motion. This is alpha, circular or rotational acceleration, is the total torque divided by mass, which is actually the rotational inertia. Again, exact same equation. It's just not linear motion, but circular motion. The definition of what is a torque? Well, it's a force applied at a perpendicular distance that causes rotation. It's a twisting force. That's how I think about it. Capital L, angular momentum. Andre, you're on your phone.
On the sheet.
Huh?
On the sheet.
What's in your hand?
My pencil.
What's in your lap?
My phone.
Were you on your phone?
No.
You weren't.
No. It was on the sheet.
It looked to me like you were staring at your crotch then.
No. Put my phone away for a while.
You would appreciate that. That's what everyone should do when they come to class. I'm begging you. I'm trying to help you. I don't want you to be wasting this time. Otherwise, what am I doing here? I'm trying to help you guys out. I want you to be focused on this. Capital L, angular momentum. Instead of mass velocity, it's rotational mass, I, and rotational velocity, omega. Same thing as impulse for linear motion. You can have an impulse for rotational motion. Instead of force times distance, it's circular force or twisting force. Torque times time. Times time, not distance. You could also have kinetic energy of rotational motion. It's not 1/2 mv squared. It's 1/2 I omega squared. Again, all these golden yellow, neon yellow, those are my unit 7. I crossed out electricity. We don't need to know about that. Units 8, 9, 10 aren't on the test. All right, so I crossed all these out. We don't got to worry about them. I left the waves because sometimes those come back in the simple harmonic motion. Right? It's like it'll give you the wavelength and speed. It might ask you for frequency for then you to use to find, say, period. So I'm going to leave these there. Geometry stuff I'm going to leave. There's likely a chance we're going to have to do triangles. More than likely. That'd be most common. Right? Sometimes it'll ask volume or stuff. But those are just kind of random. They're there. Right? Any questions about that equation sheet? So again, John, I added that, my version of this. So if you want to double check or review it later. My point in this was trying to get us familiar with this equation sheet. It's a tremendous resource, but we need to know how to use it. Alright? So I'm going to quit this and shift gears. I want us to review kinematics. I posted these PowerPoint. This PowerPoint's like units 1 through 3 or 1 through 4, whatever it is. But it goes topic by topic. Our first topic, kinematics. All it was motion. This should have a, right? So you got, if you're firing a cannonball, right? You got some sort of motion. When you fire it, is it gonna go? Yeah, it is. There. It slows down, and then it starts to pick up speed as it falls back to the earth. This motion, we can figure this out by looking at what was the starting speed. V sub 0 is like at time 0, or initially. If I know the initial speed, and I know the acceleration, and how long it's been in the air, I could tell you its current speed. At any point in time, I could tell you the speed. Other times it'll tell you, oh, I know the final speed, It was in the air for this long, and this was the acceleration. What was the initial launch speed? Right? This is one of our kinematics equations. This was straight from our equation sheet. A lot of times they're going to ask you to find hang time. They're going to give you the acceleration, initial speed, all this. They're wanting to find how long was it in the air. Plug in all the variables that you know. Solve for the one thing you don't know. Right? They really like hang time questions or projectile motion. Right? If you're in a car, the speedometer is recording your speed. Notice, your speed changed over time. Did you see the speed increasing? What is that defined as? Acceleration. If your speed changes over time, that is the definition of acceleration. That could be speeding up, it could be slowing down, or what's the third option for acceleration? Speeding up, slowing down? Huh? Turning. Remember, velocity is a vector. Right? I'm going 50 miles an hour north. That's my velocity. If my velocity changes in any way, that's acceleration. It could be getting bigger, it could be getting smaller, or it could be turning. Right? The direction of my velocity is turning. That's an acceleration. They might try to throw some tricky questions and says, you're driving a car at 20 miles an hour down around a curve. Are you accelerating? You are, because you're turning. All right, so that's something that they might throw against you. What was the average acceleration in this situation? It went from 0 to 20 meters per second in 5 seconds. What is your acceleration? Acceleration, we define as change in speed over change in time. How much did your speed change in this scenario? 20. Went from 0 up to 20. 20 meters per second was the change in the velocity. How long did this take? 5 seconds. What's 20 over 5? What are our units? Meters per second squared, or meter per second per second. Boom. That's average acceleration. Oftentimes it'll be changing, so you're going to have to use your kinematics and plug it in. What about total distance? Right? It's not going a certain speed the whole time. So I can't just take speed times time to figure out how far it went. One solution you could do is find an average speed. Right? On average, you were going 10 meters per second times 5 seconds. You went 50 meters. Sometimes you can use averages to approximate things. Not all the time. It's not always going to work. Here's an example problem. Stone, you're up here on this cliff. You throw it up with a speed of 12 meters per second. What happens at the very tippy top? What's its speed? 0. That's when it stops, and then it starts to fall all the way down. The cliff is 70 meters tall. How long does it take to reach the bottom of the cliff? Right? So you would go to your kinematics equations, the first 3, and realize, okay, I need change in position. It's talking about position. I need initial speed. And I need time. So you're going to look at these equations. Well, the first equation doesn't have position, so that's not going to help me. I could use any of the second 2. I'm going to use the middle one. What was the initial position? Right? Threw it off a 70-meter cliff. So it started at 70 meters. The final position, it hit rock bottom. It went all the way down to 0. The initial speed was 12. How long did it take? I don't know. I leave it as a T. Plus 1/2. What was the acceleration in this direction? 9.8. It's gravity. Remember, this is positive y. So if gravity is always pulling things down, it's a negative number. It's not accelerating in the positive direction, it's the opposite. So you will need to put a negative 9.8, and then time I don't know. This is an algebra equation with one unknown variable. Now it's quadratic, but when you solve this, you would get 2 answers. One of your answers won't make sense. One of your answers, will probably be like negative. Does it take negative 0.5 seconds? No, that makes literally no physical sense. So you know that is not a solution to your equation. You solve for t. You guys remember graphs? We have position time graphs, speed time graphs, and acceleration time graphs. Notice, if I'm accelerating at a constant rate, that means my speed has to be increasing at a constant rate. Yeah, it'd be quadratic.
Yeah.
But if I'm constantly speeding up, I'm constantly covering more and more and more and more ground per time. So you're going to have to remember the connections between position, speed, time. Question or stretch? Okay, sorry. Acceleration is constant. At any point in time, you are accelerating at 10 meters per second squared. That means, again, acceleration is change in speed over time. The velocity is changing by the same amount every second, because your acceleration is constant. When you have your velocity time graph, you see, the speed is going up at the same amount every single time. So that means the faster you go, the more distance you cover. Right? If I'm going about 45 miles an hour, I cover a lot of ground really quickly. But when I started, I was only going maybe 5. I don't cover a lot of distance in that 1 second. You see that here. In the beginning, your position isn't changing much. But the faster you go, the further you cover in a certain period of time. Okay? Remember, the change in position over time is speed. So if you find the approximate slope, is this a steep slope or not? No. So is your speed high or low? Low. Your position's not changing with time very much. That's the definition of a slow speed. Now up here, rise over run, that's a pretty steep slope. You could quickly see I'm going faster here than I am here. It's not the distance itself, it's the rate of change of the distance. I don't know how often you'll have to do this, but acceleration time, if you find the area, that's like taking acceleration multiplied by time. Acceleration multiplied by time tells you speed. So you could figure out what the speed is here. Notice, any section, your area is going to be the same because your speed is the same. The one that you will likely see is this one. It's going to give you this and tell you how far did it move from here to here. You're like, well, I don't know. You do know. If you take speed over time, speed is distance over time. If I multiply speed by time, guess what? You get distance. We call that displacement. The area right here is the total displacement from this point to this point. That's at 2 seconds. Whatever this number is should be my displacement at 2 seconds. Whatever displacement from here to here, this area should be this distance. Again, when it gives you numbers, right, those numbers will match up. Slope is velocity. We talked about that. Your position isn't changing much with time. You're going slowly. Your position's really changing over time. You're going a lot quicker. I kind of give it away. What do I do if I'm trying to find the total distance for this chunk of the graph? Huh?
Like the x times the y.
This x or this x? Or excuse me, this x. Which one?
The bottom.
Times what? This y or that y?
Say that one.
This one?
No.
That would be this whole box. I don't want that area. I want just the blue area.
So the bottom times that first one.
You're saying take this times this? Okay, that gives me this little rectangle.
And then also do the triangle.
Then you got a triangle,
So-
right? Then I have two simple geometric shapes. I could find this area, add it to this area. Both of those are really simple. Good. It's very likely that you'll get a question like that. They want you to show us that you know how to read a graph, what the graph means, and then how to answer a question. This is y times x, 1/2 y times x. Be careful. The area of this triangle is not this height times this base times half. Your triangle starts here and goes up. Your height is that minus this point. Okay? That is your height. Not this number. Because that's here to here. That'll be another thing to keep in mind for a scenario like that. This is actually how you get one of your kinematics equations. 1/2 at squared, v naught t squared. Distance is change in position. That's how you get one of the equations. In this situation, when I roll a ball off the end of the table, which path does it take? Trick question. It doesn't take either of them. A marble doesn't just continue off of the table. It also doesn't immediately fall as soon as it leaves the table. It does both. Right? When we have two-dimensional motion, that's what we call projectile motion. There's motion in the x direction and motion in the y direction. Notice that as you go in the x direction, is the speed changing? No. Every second it's going a set amount. It's a constant speed. What about in the y direction? You see it getting faster and faster? Why is that?
Gravity.
Gravity. Gravity always accelerates things. So if you combine those two, the x ball and y ball, they cross over. That creates the actual motion. It's going to keep moving in the same x direction, or x velocity. As soon as it leaves the table, gravity will start accelerating it. That's why it creates that projectile, the parabolic motion. And again, it's just showing you where you get some of these equations from. This is the acceleration.
Can you discuss the physics of braking an elevator?
Braking an elevator? Do you mean like jumping while it's moving?
Wait, so you guys jumped in it?
I'm pretty sure you shouldn't be able to brake an elevator.
Wow.
Elevators are engineered to be like 5 times stronger than even the weight capacity.
Is that a challenge?
If you broke it, you probably triggered, they have like seismic fail-safes. If it senses too much crazy motion, it freezes itself up. It locks itself into place. Is that what happened?
No.
I don't think so.
Because if it snapped and fell,
No, it didn't
people
snap.
probably got hurt or died.
No.
That's why they're over-engineered so much.
Well, they
John
got
and I
brakes
were
on them,
stuck in
so
Yes,
they got brakes on them, so they.
but if the cable snapped, nothing is holding that elevator up.
I know that's what I'm talking about.
Yeah, I
If
know
the
it
cable
has- I know it has
snaps or
brakes,
they fall, they got brakes that stop it from.
Do they?
Yeah, they
think
do.
so.
I think so.
If so, that might be true.
Pressure up.
But that would be like,
Also, like every
again, a secondary fail-safe.
Yeah, because like I think it, like they figure out like if it starts like free falling, then there's like a sensor that like climbs down on like metal bars to the side of it.
Okay. Could be. I was always told that elevators are rated for basically like 5 times of whatever they're supposed to hold. Because if idiots like, 5,000 pounds, that means 5,000 people, and they try to do something stupid, right? Engineers can't risk that on an elevator where people could die. So they try to cover up for people's stupidity by I'm serious, they over-engineer so that stupid people don't kill themselves using their products.
It's called natural selection. Yeah, that's exactly what it is.
Regardless. All right, so I'm going to pause here.
Government doesn't like natural selection. They want you to.
This is a good point. Sometimes questions will give you a projectile motion, and they'll ask you to figure out, like, how long is it in the air, or how far does it travel, right? You need to remember, projectile motion is 2 directions. There's an x direction and a y direction, right? How long is it in the air? All you care about is the y direction, right? How long is it before it touches the ground? Once it hits the ground, it's no longer in flight. That can tell you the time it's in the air. Then you're like, well, during its time in the air, the speed in the x direction doesn't change. Nothing's accelerating. So I take that speed times the time. That's how far it went. Also, quick tip, if it ever asks you, like, for a certain speed, what angle gives you maximum distance? 45 degrees. It's a quick tip. That has to be assuming it's the same launch speed. If you change launch speed, right, you got to actually do the math to see, well, I don't know which one's actually in the air more. But for a set speed, 45 degrees gives you max distance. All right, so I'm going to pause there. That's my kind of lightning refresher for all the key concepts and things that you're going to see on kinematics questions. Now, the big thing is going to be, okay, can we actually use those? So, I have this posted, so if you want to go back and look at this in your own time, great. What I want to do now, I got like 20 minutes. Would you guys rather do practice multiple choice questions? The answers are given, but I could show you like how to solve them. Or would you rather save that, do on your own time, and do FRQs in person, and then talk about them?
We have time to do FRQs in person and then talk about them in 20 minutes.
Yeah, most FRQs are only like 10 minutes, right? If an FRQ question is about 5 minutes long, or excuse me, 5 questions, they go quick, right? That'd be 10 minutes.
Chicken was here 2 evenings.
Like last time they
That's FRQ.
Yeah,
I did. Ended up not even being on the test.
Oh yeah, we'll be done
You want to do an FRQ?
Yeah.
Okay, so what I have, I printed these for you guys. I actually have one kinematics and one dynamics. So we'll just do the kinematics on the front. So I'm going to pass these out to you guys. Again, I need to confirm exactly how many points this one is so that I can give you guys that time estimate to help yourself figure out the pacing. Because again, the pacing is important. Because you're going to want to be able to time yourself, keep yourself on track. Okay, so you guys are going to be doing, again, this is posted, this is the, right here, Unit 1 and 2 FRQ.
1993.
The first one, yeah. I don't know if that is the date of this question.
Okay, great.
I'm suspicious, huh? Yeah, I'm suspicious that it actually is a legitimate date. Like this question came from the 1993 AP Physics test.
1985.
Yeah, I don't know how long, I'm not 100% sure, but regardless, this question, $1993.
Either way, it's overdue. We should do it.
Wait till I start.
The problem
Either
is
way, I
already-
can't do it. So, okay.
These ones, the grading isn't as precise as we're used to.
Which one are we doing? The front?
The kinematics, the front one, so the 1993 one. Dynamics we'll keep and we'll do next time. This question I think is like 7 points. Actually, probably about 6. So that would mean roughly 12 minutes. All right? So I'm going to set a timer for 12 minutes to let us experience what kind of a pace we should be at, and then we can go through the answers, which I have up there. Don't look.
It's okay,
Okay, good. All right. So again, go ahead and get started. Use your equation sheet, right? Use scratch paper. Use the calculator. All those things will be available to you. Make sure you use them when you need them. I'll set an alarm. I'll do 11 minutes, 30 seconds. Okay. Yeah. I'm running out, but
I can.
and again, we're doing the kinematics. We're doing that. Yeah, that was Unit 1. Yep. So we're only doing. Yeah, only doing that kinematics right now. That'll be about a 12-minute question. We'll save the dynamics FRQ for next time. about halfway, just to keep the pacing or the progress in your head. All right, so that would be time. That would be roughly right at the pace that you would need to be moving at, finishing this problem so that you can keep working on the rest of those FRQs. So just so you, again, are building that feeling for what kind of a pace do I need to be keeping up for this problem. Oh, I probably need to reconnect this, don't I? Dang it. Did anybody get the I, the first part of it, the speed at the end of each of those intervals? The first interval should be pretty easy. It didn't move. Again, it started at 0 meters, started with a speed of 0, and it didn't accelerate. Literally nothing's happening. So from 0 to 5, you have 0 meters per second. That's, again, it's the speed at the end of that interval. What about the interval between 5 and 10 seconds? You'll notice it's accelerating. It has a constant acceleration for the entire period. That acceleration is 4 meters per second squared. What that means is every second that goes by, the speed increases by 4. So you could mentally have done it, right? Well, 5 seconds, what's 4 plus 4 plus 4 plus 4 plus 4? What do you get? Or what's 4 times 5? 20. I said it 5 times, right?
No, just too many for me to comprehend.
Okay. So at the end of, at 10 seconds, the speed has risen to 20 meters per second. You could also done your kinematics equation. Velocity equals initial velocity plus acceleration times time. You could have done that. It'd give you the same thing. What about from 10 to 15 seconds? What's happening? What's going back down?
10 to 15. It's not.
The acceleration went back down. What is the acceleration between 10 and 15? What's the value of the acceleration? Look at the graph. From 10 to 15. 0. There is no acceleration. So whatever speed you started with, that's what you end with. Your speed is not changing, so you maintain 20 meters per second that whole time. Now, Brody, what's the speed between, or the acceleration, 15 to 20? Negative 4, right? It's negative 4 the whole time from 15 to 20 seconds. Right? So again, you could do your kinematics. Speed equals initial speed, 20, plus acceleration times time. That's a negative 4 times a 5. 20 plus a negative 20 is 0. You come right back to a stop. It asks you to plot that on a graph. When you're drawing this, this is where it gets tricky. You did some math. So some people are going to be like, oh, let's plot those points. Right? At 5 seconds, time.
Really?
You start at 0 speed. Right? What's your speed at 5 seconds? Oh, at 5 seconds.
At 5 seconds. Our speed?
Yes.
We still got practice.
Guys, what is the speed at 5 seconds?
Still 0.
It's still at 0.
Oh.
The whole time from 0 to 5. No speed, no acceleration. It's not doing anything.
Yeah, I put that. I'm just dumb.
Yeah, it's tricky. Because the intervals is the speed at the end of that interval. At 10 seconds, you're up to 20. At 15 seconds, you're still at 20. Now at 20, you're coming all the way back down to 0. Now some of you guys are going to be like, dun, 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 dun. Is that right?
What'd you do?
You connected dots. Dot to dot to dot to dot to dot.
Yeah.
Is that right?
I think so.
This one's easy, right?
Yeah.
Whatever. But from here to here, this goes up to 20.
Mhm.
What kind of increase is it?
It's linear.
It's linear. The acceleration was constant. It's changing at the same rate. So it is literally just a line. It's not a curve. It's not a curve. It's not a squiggle. Might sound trivial for this example, but some of them could be tricky. Here to here, no change in speed. We got a constant acceleration for the last section, don't we? So the change has to be steady the entire time. That is your graph for part A, or part I. The second part's asking for displacement.
I don't mess this one up because I think it's
The first one?
yeah. Well,
Okay.
I didn't realize that the acceleration just
Yes.
stopped.
The acceleration here goes to 0. So that just means your speed stops changing. You're going to get steady. When you calculate displacement, what you could do is use this answer and find area under the curve. The displacement here to here is 0. The displacement here to here is this area. Displacement here to here is this area. Displacement that area. That would be an easy way, and then you're going to have to plot that. What's the displacement at what point in time? Guys, homework. Your guys' homework. I need you to go to classroom, the workbook, AP Physics workbook. Each section, right? Actually, this one, I might repost it for just Unit 1. Pick 10 questions, 10 multiple choice, solve them, check your answers, and bring them back. Okay? I'm trying to keep it easy to start with. 10 multiple choice should take at most 10 minutes. So again, it shouldn't take too long, but we want to keep them fresh. Yes. Oh, Danny, you're doing tests already?
Yeah, can I go to my H class and then come back?
Yes, you should go there first to check in for attendance. Once they got attendance, if they had announcements, whatever, then you come back down here. Thank you.
I will stay. But no matter what, I'll stay. No matter what, I'll stay. Isley, can I go to Aaron? Or to work on work?
Yes.
Okay. I go down to the rush. Yeah, for attendance.
Yes, you can. Thank you. Yeah, again, hold on. Let me do attendance. I don't think I have announcements, but I'll turn y'all loose.
Hey, will they be passing out sign-up sheets for blood drive in this class?
They sometimes do, but I don't know. It's never on a schedule that I know. It's usually pretty random. So they might. Are you wanting to sign up?
Yeah.
Yeah, well,
Let's do it.
You gotta leave this class here?
Yep, that's exactly.
If after we do attendance and stuff, I could send you to the office just to ask them, like, hey, I want to sign up for the blood drive. I don't know where. They might be able to point in the right direction. Well, just hold on a sec. Let me do attendance, and then I can send you down there if you need it.
it's so cold.
Did Ian scream class? 'Cause he tried to-
Oh, dang it.
She'll take it this time.
Yeah, but you need to fill them out because I don't write it.
I heard that you